in the last few decades. And these have really fundamentally changed how the system works. So one is the proliferation of water weeds in the delta. We've had particularly Aguirrea densa, which is the Brazilian water weed. We've got a few others, but we don't have very good monitoring data that I know of to show how the abundance of these water weeds have changed. But we do know that largemouth bass are really tightly tied to water weed sorts of weedy sorts of habitats. That's where you go to catch them. And one good long-term record we have is from the salvage facilities, and we have largemouth bass, young largemouth bass, showing up at the salvage facilities over time. And what you see basically is before the late 80s or so, essentially none, and then ever since then we see sometimes huge numbers, in all years quite a few. So that's an indicator that yes, around 1990-ish. There was a change to this, or a beginning of a water weedy kind of environment. And we have a similar thing going on with the toxic microalga microcystis, which we think started increasing around 2000. And this species, again, it's a toxic species. It seems to be causing, or could be causing, harm to some of the aquatic organisms in the system. And its abundance probably increased, again, around 2000 or so. And it's very abundant in summers and falls. It's abundant right now out there. Interestingly, in 2011, when we started our microcystis study, it was almost not to be found out there. Luckily for us, this year we're getting plenty of it. Going back to this Aguirrea situation here, we're also seeing the proliferation of another water weed in the system. It's actually a native, but it was formerly not found in the delta, and now it's quite abundant in certain places like Frank's Tract. So we think again that some of these changes are due to the steady flows that we see in most summers and falls, and that doesn't necessarily imply that any manipulation of flow would reverse that, and so we don't actually know whether that's the case or not. So to summarize, the shape of the salinity field, the shape of any salinity range you want to pick, the depth, the mean depth, and the area, which are important for a lot of organisms like phytoplankton and delta smelt. These all vary with flow. Pelagic species that inhabit those regions live in a dynamic habitat that's always moving, and they're moving with it. The low salinity zone is a key region for some species, and it's also habitat for other species. May not be the most important habitat, but it is an unproductive region and heavily subsidized from other parts of the estuary. The abundance X2 relationships that we've known for several decades are not all about the low salinity zone proper, and then simple relationships can be misleading, and sometimes we see rather complicated sort of looping causal connections in the system. Thank you.
I want to thank the members of the board for this opportunity to speak to you today on this really challenging problem that you're facing. Is this okay? Is this better? What I want to do today is I want to pick up on the themes of the talks that you've just heard from Bill Fleener and Wim Kimmer. The theme of this estuary as a highly dynamic, ever-changing ecosystem. I want to say a few words about change, future changes, what the implications are for policy to protect estuarine habitat. I want to talk a little bit about the role of science in this problem, and then I want to end with a suggestion, a recommendation to the members of the board. So I want to begin with a couple of foundational principles of how estuaries work as ecosystems. And I'm starting with this example from an estuary on the west coast of Denmark, because it's a nice, clean example. So this is the Ringkøbing Fjord. This photograph shows the estuary in the bottom. It's connected to the North Sea through this single opening. And a decision was made in the 1990s to change the operation of this sluice gate that controls water exchange between the North Sea and the estuary. And you can see in this bottom left panel the seasonal cycle of salinity, but the shift up as a result of this enhanced exchange. And on the right-hand side, you see changes over time in the abundance of three different kinds of organisms. So on the top, that salinity increase was apparently enough for the estuary to become colonized by a clam, by the soft-shell clam Maya arenaria. So the panel here shows the increasing biomass of this clam. Now, you know that clams are filter feeders. They process large volumes of water. They remove phytoplankton from the water. The middle panel here shows exactly what we saw in Suisun Bay in 1987, the shift down in the amount of phytoplankton measured as chlorophyll. There were lots of other changes in the estuary that followed, changes in water transparency, changes in the communities of plants that live on the bottom, including plants that produce the seeds that are a primary food resource for diving ducks like pintails. So you see population decline of pintails. I picked this example because it's a nice, clean example that illustrates two important points. The first one is that human actions can change salinity in estuaries. And the second is that what appear to be small changes in salinity can bring about large biological changes at multiple trophic levels. Okay, the next example, the next principle that I want to talk about is this principle that estuarine ecosystems can also be transformed by shifts in the climate system. And here I'm showing an example from San Francisco Bay. And I'm showing data from Central Bay, combined data from Central Bay and the South Bay. On the right side, these graphs, the blue and red lines, show indices of the abundance of 4 different communities that live in the bay. On the top is a community of bottom-living fish like English sole. Below that is abundance of 3 different species of crabs that migrate into the estuary from the coastal ocean. Below that, shrimp. These are all data collected in this wonderful Bay Studies monitoring program that's conducted by Department of Fish and Game as part of the IEP. And below that are changes again in chlorophyll, measured an index of phytoplankton biomass. This is measured as part of our research program at the USGS. And what's really striking in this graph is the same pattern in all 4 communities. That is 2 decades of relatively small abundance or biomass. These records go from 1980 through 2010. So 2 decades of one kind of pattern, and then this abrupt shift up that happened sometime after 1999 to record high abundances of these bottom-living fish, crabs, shrimp, and phytoplankton biomass as chlorophyll. What's really intriguing about these patterns is that the shift up in abundance coincided pretty closely in time with a shift in the pattern of climate forcing across the entire North Pacific Ocean. So the Northeast Pacific Ocean shifted from its warm phase that it had been in for decades, including the first 2 decades of observations, to its cool phase. And we think we have pretty good ideas about why these shifts happen. But I picked this also because it's a really nice, clean example of how biological communities can be completely restructured as following shifts, large-scale shifts in climate forcing across ocean basins. The third principle is one that you know very well and is the reason why we're here, and that is that the Bay Delta ecosystem has been transformed by the cumulative effects of human actions and climate variability. So we know, for example, this near complete transformation of the landscape that began in the 19th century. This is a wonderful study that Alison Whipple and her colleagues at SFEI just released. Water development, upstream use, and diversions have had an effect on water, on the water balance of the estuary, so that now exports constitute a median 30% of inflows to the delta. This middle panel here shows long-term trends of suspended sediments in Suisun Bay. The suspended sediments are the important component of turbidity. That has been reduced by half since 1975. The right panel is kind of a reprise of this composite diagram that Wim showed you, the effects of introduced species, just profound reorganization of biological communities after the clam corbula or Potamacorbula became established in 1987. And we think that there are links between the success of species introductions and natural variability in the climate system. So this figure from Bill reminds us that we had this multi-year drought in the late 1980s. That was the period when Potamacorbula became established. So we understand that this is a place that has changed remarkably over time. The Bay Delta ecosystem that exists today is very different from the Bay Delta ecosystem that existed when I started studying it in 1976. And some of the biological communities are unrecognizable from the communities that existed at that time. Now, there's no reason to think that these changes have ended, and in fact, there are reasons for us to think that the estuary will continue to change, but perhaps in different ways, because new drivers are coming into play. So we think, for example, we wonder, how is this Bay Delta estuary going to respond to changes in the global climate system as the century unfolds? What are going to be the ecological and infrastructure implications of introductions of new species? We're particularly concerned about the quagga mussel because it has disrupted ecosystems and water infrastructure in other places where it's become colonized. We're talking about new conveyances that are going to have a big effect on changing water flow paths across the delta and into the bay. We're considering and thinking hard about scenarios of catastrophes that will breach levees and flood islands in the delta with profound effects. Wim told you that we have this toxin-producing cyanobacteria that's forming blooms in the delta. These are forms that are adapted to high temperature. One scenario that we need to consider is that as delta waters warm through this century, that's going to select even more, favor even more habitats for the production of these toxin-producing algae. So for you, for the members of the State Board, what does all this mean? And as a scientist, I think one of the implications of this is that we need to be thinking about policies that are going to be durable. And by that I mean policies that are going to be relevant and effective into the future, that take into account these kinds of changes that we're anticipating. So in order to do that, in order to establish durable policies, we need to be able to anticipate changes in the future, and we need to build in contingencies into our policies so that they adapt to these changes when they occur. Okay, so what's the role of science here? I want to suggest that we have two roles to play here, and are playing. The first is that we have the capacity to build tools for anticipating change in the future, and this is something that we're doing now. I'd like to give you an example of one. This schematic shows a large-scale project that began a number of years ago in which a group of us got together and tried to link different kinds of models in a way that hadn't been linked before. So the process began with outputs from global circulation models. Those were then used to drive watershed and water operations models. Those were then used to drive inflows to the delta to drive hydrodynamic models. And at the same time, we were using statistical models to assess the acceleration of sea level rise at the entrance to the estuary at the Golden Gate. So the outputs from this exercise look like this. These are visions of the future using that approach, using a specific set of models and a specific set of scenarios of greenhouse gas emissions. And we chose two scenarios. In the red, a scenario of faster rate of global warming, and to the right, a scenario of a slower rate of global warming. And you can see that these are projections that go from 2010 through the end of this century. And this kind of modeling analysis suggests that we need to consider the Bay Delta in a climate system that warms progressively over time. It might be drier, but we don't know. Here's an important area of uncertainty because the models don't agree about whether California's climate will become drier or wetter. They do agree that sea level will continue to rise, and in fact, the rate of sea level rise will accelerate. And one of the implications of that is that if everything else is held equal, the estuary will become saltier. As the sea level rises, that pushes salt further into the estuary, and so a plausible scenario of the future is a saltier estuary. So we did this exercise, we did these kinds of projections because we thought that they would be useful for policymakers to start thinking about the future, anticipating it, what this means for building contingencies into policies to protect estuarine habitat in the system. So how specifically can these projections be useful? Let me give you one example. This is a relationship that you probably know pretty well. The black solid line here is a fitted regression line through many, many different observations, those little black dots, that shows the contemporary relationship between flow and salinity measured as X2. So you know that as flow increases, salinity decreases, and X2 becomes smaller. The challenge that you and we face is that this is not a relationship that's necessarily fixed in time. Because the estuary is dynamic, this relationship is also going to be dynamic. So as, for example, as sea level continues to rise and salt intrudes into the estuary, that means that this relationship is going to change and it's going to shift to the right. What that means is that if one of the policy goals is to maintain salinity in a particular range, we know what flows are required to meet that salinity standard, that the amount of flow in the future that's going to be required to meet that salinity standard is going to be higher. And in fact, our colleague Bill Fleener has done some calculations like this under different scenarios of sea level rise. So we have tools that allow us to build scenarios for the future that you can then consider in thinking about how can we build contingencies into our policies. The second thing the second role of science, the science programs, is to make observations, both through our research programs and our monitoring programs. So as you know, we have wonderful programs of biological monitoring, at least in the northern part of the San Francisco Bay system. We have excellent monitoring programs for hydrologic quantities. We have very good water quality measurement programs. So, and this is important because we need to keep a pulse on the estuary to detect the kinds of changes that we're anticipating as possible future scenarios. The fundamental problem that we have, I think, at this point is this one. These three components are only weakly linked. They are linked, but they're not as strongly linked as I think they need to be so that we can build durable policies. So I'm talking about the components of policymakers, you guys, and two components of the scientific community, the community that is building these forecasting models that we can use to anticipate future changes, and the community of scientists and engineers who are running observational programs that are required to detect changes in the future. And I think that there is a there is a limiting factor to our ability to use science now to inform policies so that they can become durable. And I think it's this weak coupling that's the limiting factor. But I think there's a solution to this. And I think the solution is to create new processes that allow stronger coupling between policymakers and the scientific community. So let me kind of, this is my last slide. Let me kind of walk you through these arrows that flow in both directions and represent processes that don't exist now but I think are required to solve this rate limiting problem that we've got of using science in an adaptable way. So for example, when we think about an arrow going from policymakers to forecasting models, one of the ways this might happen, for example, would be to create a process so that policy-making bodies like yours can compose a list of the highest priority questions or problems. Can you use models to develop these scenarios that we need to start thinking about contingencies in the future? And in essence, a process that allows you to shape the kind of science that's done by these groups of scientists and engineers so that the information that's being produced by forecasting models meets your specific information needs. And you see that this arrow is going in both directions, so that means that the flow of information also should go from the models to the policymakers. So when new results appear, they've been analyzed, this group can then inform you and your staff of what the answers to those problems were, give you specific scenarios, answer specific set of questions that you've posed. This arrow on the right here represents the need for stronger coupling between these two groups of scientists, those who are doing the forecasting models and those who are making the observations. And one of the reasons why we need to strengthen this, for example, is that I think of the forecasting models as producing hypotheses. These future visions, we can't predict the future. They're future visions. We should take them as hypotheses. Those hypotheses need to be tested with data. And as wonderful as our monitoring programs are, I'm not sure that they're perfectly designed to measure the right things at the right times at the right locations to test these hypotheses. So I think we need to institute new processes of information exchange between these groups of scientists. And then lastly, we should think about instituting processes that strengthen communication between those who are running the observational program and the policymakers. And in the next talk, you're going to learn a little bit more about what we're doing in that regard. So here's my suggestion. Here's my recommendation. My recommendation is that that members of the State Board consider using your power and influence to marshal the resources so that we can establish these processes, to establish a stronger working partnership between the scientific community and policymakers so that we can build durable policies. Thank you.
I hate to inform those at the back, but you really are going to have to find a place to sit because it's going to create a problem for us if you don't.
And regrettably, there are no more empty seats next to Mr. O'Loughlin.
All right, the mouse has been passed. So my name is Anke Müller-Solger. I'm with the Delta Stewardship Council as the lead scientist for the Interagency Ecological Program, and my co-author for this talk is Larry Brown with the USGS, who is sitting right next to me and can also answer questions. And I will shift gears a little bit from the results that the previous speakers presented to how this might all affect science and also policy in practice here and now. And so to recap really briefly what the problem really is, as the previous speakers presented, we have a lot of change in the system in the past, now, and into the future. We have lots of drivers that affect the ecosystem. All of that adds up to a very uncertain future. Uncertainty is here with us to stay, and if you add to that the weak couplings that Jim Klern just talked about, you end up with what many have called a truly wicked problem. Actually, Mike Healy, the Delta lead scientist, CalFed lead scientist before Peter Goodwin and Cliff Dahm really like to talk about that one. Anyway, what's obviously needed is a new approach to deal with such a thing, because so far we've mostly produced trouble. The obvious approach that many people are talking about is adaptive management. I do think it's the appropriate approach because it's in fact intended to deal with uncertainty, to manage in the face of uncertainty, and to also couple in a much more systematic way than previously done science and policy and management. And it's doing that through management of resources, actually active manipulation of resources that is intended or is also intended to really help learn things. So for this more active type of adaptive management, learning is built right in, and that's a really important part of it. This is the figure from the draft Delta plan, almost final, that Felicia Marcus knows really well. The Delta plan, of course, like many other plans now in the estuary, is heavily relying on science and adaptive management. And it has this figure in it to show the adaptive management cycle, which consists of 3 phases. First of all, planning, which is where most of the policy also happens, and then doing, which includes management or manipulation of resources and scientific exercises, and then that goes into the observational phase, where a lot more of the science happens that then eventually might lead to adaptation of the policy and management approaches. And this is not a new thing per se. What's really new is that it's being not just talked about more here and included in many of the plans and reports. For example, your 2010 reports on flow criteria had, I think, 63 mentions of adaptive management. I actually counted that. So it's talked about a lot, written about a lot, but it's also starting to be implemented. And that's actually the new thing that I want to talk about. And one example of that is the adaptive management of fall outflows. And this is what I'm going to talk about next. And it's not just an example, I believe, it's also sort of a local test case of something that is actually, as the review panel that just reviewed all of this said, perhaps one of the highest profile and highest impact ecosystem manipulations in the country, or even the world. Those are their words. This panel, by the way, deliberated, or we had a workshop about this in the end of July, beginning of August, and they just finished their report. It was just sent to the Delta Science Program yesterday. It should be on the internet pretty soon. But anyway, this is just for your information. This is obviously then an interesting case to see if this type of adaptive management, as the Delta plan here has it, actually kind of works in practice and how this might go. And also, of course, you in your own flow criteria report said that it should in fact be implemented within an adaptive management framework, this fall outflow management. So this fall outflow management was actually required by the 2008 biological opinion about Fish and Wildlife Service, Delta Smelt biological opinion about the operations of the Central Valley and state water projects. And then the Bureau of Reclamation put out first in 2011 and then again a revised version in 2012 an adaptive management plan, and you can see the top part of it here. And so I'll talk about what's in that plan, and then I'll talk a little more in depth about the science that's going on within that. And I'll simply take you now through the different steps involved in this cycle here. I'd like to note that the actual Bureau of Reclamation Adaptive Management Plan uses a slightly different version of that, which is put out by the Department of the Interior. This one here has 9 steps. The other one has 6. This one's a little more in detail. I like it. I suspect others do too. Plus, you know, it might become an important piece that we will use, all of us here in California, into the future. So let's see how it goes. So starting with the problem, Delta smelt, as I'm sure you know, are an endangered native fish species here in the system. And this, along with lots of other things, put some constraints on water supplies for human use. The goal, of course, is to improve the status of Delta smelt and hopefully also then make things better on the water supply side. And importantly, in this more active adaptive management approach that's been taken by the Bureau of Reclamation in its adaptive management plan, the goal is also to learn, because there are many uncertainties associated with this particular action and in general with flow effects, as you know, on the ecosystem and particular species. So this is a very important part, and right up front, that we want to learn more about these things by doing this action. The next step in this adaptive management cycle is to model linkages, and in this case the U.S. Fish and Wildlife Service in its biological opinion, and then later the folks at Reclamation in the adaptive management plan used a whole set of statistical and conceptual models to relate flows to Delta smelt indices. And then the Fish and Wildlife Service came up with this particular action about the fall, which is of course only a part of a suite of actions in that biological opinion intended to well, help smelt somehow. So what it said right there in the biological opinion was that in falls after wet springs, the X2 is supposed to be at 74 kilometers, which is about Chips Island, and puts the low salinity zone relatively far to the west in the system. And in above normal years, it's supposed to be slightly farther east at 81 kilometers. In all other years, there is no action. So this only applies to wet and above normal years. So then the next step is actually action. And since this only applies in wet and above normal years, the first wet year after the biological opinion was issued was actually 2011. And you probably all know that it was wet. The action didn't really happen as intended. It wasn't implemented that way because, of course, there was some court action going on. And there was a court order to not implement the action in this way as far as the X2 part of it was concerned, although the adaptive management part was supposed to stay and actually happen, and it did happen. However, we actually did end up with an X2 that was almost as low as was what had been written in the biological opinion. It was actually at 75, which you can see here on this graph. So to orient you on this graph, obviously the years are at the bottom. Average September, October X2, which is what's often referred to as fall X2, is on the y-axis. And of course, the farther, the lower the numbers, the farther west X2 actually is, and the higher the numbers, the farther east. I indicated here with this purple line where 75 kilometers is, which is right there where that arrow on the map points at Chips Island. And when X2 is around that area, then most of the low salinity zone, as the map at the top, which was produced by Michael McWilliams, similar to the ones that Wim Kimmerer showed, is overlaying Sassoon Bay and Honker Bay for the most part. And another thing you can see on this graph is the wetter years in blue and the drier years in this, whatever that color is, orangish. And so what you can see, if you look at this a little more closely, is that before the mid-1980s, and remember all the different changes in the ecosystem that happened after the 80s, although I'm not jumping to a simple conclusion here about that, but still, before the mid-1980s, we had this rather variable regime of wet years where X2 was west of Chips Island, and then drier years where it was east of Chips Island. And then after that, we had a succession of years where we only had 3 instances, really, of X2 farther west than Chips Island. And otherwise, even in wet years, X2 was fairly high up in the estuary, and it was overall more stable. And actually, one more point on that is that, quite importantly, we do need to have signals like that, and we haven't really had them lately to actually even observe possible effects of the low salinity zone being either farther west or east on all these ecosystem parameters that we're interested in on all the species. So obviously that we had it in 2011 was a great chance to actually learn something. And this is where the next phase of the adaptive management cycle comes in, which is all about the observations that Jim Klern talked about earlier. And in this case, it's actually the study, which we have now called the Fall Low Salinity Habitat, or FLASH study, is conducted under the umbrella of the Interagency Ecological Program, IEP, so I actually know something about it. And it's really quite simple as far as the questions that we're asking. So it's obviously about the effectiveness of the action. It's about the mechanisms and processes that we're very interested in, which is what Wim Kimmerer was talking about. And it's also about if there are perhaps other options for actions that might come out of these new insights that we're gaining by doing this. And so quickly, what we learned, or what we did in that first year, we had a conceptual model that was very important for the study that lent itself to producing predictions for 3 different scenarios of X2, 93 of them. We put a lot of people into the water and into labs to make observations to test those predictions, and so far we have 17 predictions that were supported by the data. We have 9 that weren't, and the rest is still either in progress or unclear, or there is simply no data. And then modeling also plays an important role, both in the setup for this and then in the analysis and synthesis phase, and I'm sure we'll do much more of that as we gather more data. We have at this point a draft FLASH report written by Larry Brown here, which was recently reviewed by this Delta Science panel that I already referred to. And their first observation when they reported out to the audience was that this is difficult because so much is going on. This is Denise Reed's handwriting there. But they also had some more profound observations than that. And I'm just going to quote a few things that resonated especially with me from that report that was received by the Delta Science program yesterday. So they did say that it was an impressive mobilization. My personal comment on that is that yes, but it was really by and of already busy people and is probably not sustainable that way. They said that learning from such an extensive effort will take time, more than just that 1 year, and we need more years that have that kind of signal as well as other signals. They said that there's no fatal errors, but room for improvement. For example, leadership, this is really important. There's currently no chief scientist and certainly no real dedicated support staff for this thing. And they said there should be such a thing for at least 10 plus years. So this is a real resource issue for doing these sorts of adaptive management things. Linkages, they talked a lot about this and that we really do need more integrative modeling and also need to pay attention to other seasons and other processes, et cetera. And with that, I actually want to go through briefly through other seasons for delta smelt, but I'm looking at Brock and the time, and I'm actually wondering about that a bit.
Yeah, this panel is supposed to end at 10:45, which is 15 more minutes, and we wanted to give the board staff time for questions.
Okay, so I will only say that there are other seasons that matter too, and in 2011 things lined up just beautifully apparently, but other years that isn't so. And we need to think about that too, and we're trying to do that actually with a with another IEP group called MAST, but I don't have time to tell you what that is. So my lessons for all of this is that obviously the couplings that Jim Klein talked about are super important in order to make such a thing work. In this case, it involved a large amount of people from universities, agencies, private, etc. They all need to be organized, and all the data then needs to be put together, etc. And all of that obviously needs time, more than just 1 year. It's difficult after all. It needs a year-round and integrative approach. It needs assigned funded and knowledgeable leaders and staff. The magnitude of the different phases of this adaptive management program, I think, need more attention in terms of how much we do of each and how we fund each of these parts. And then finally, I didn't talk about it because I think this is something we really have to work on, is what does the response, the adaptation, the anticipation really, how does that really work for us? So with that, I let Cliff Dom do the final concluding remarks, unless you have specific questions for me right now. Okay.
Okay, I'm doing a quick time check, and it's clear that I'm going to need to truncate a few of my comments, so I'm going to make a few comments. I've typed them out, and I can provide them to you, but I want to leave you some time to ask us some questions, so I'm going to give you the Cliff Notes version of my presentation so that hopefully we'll have a little time for discussion. One point I did want to make before I launch into my comments is that the panel that you see surrounding me here, the four that just presented to you, have over a century of direct research experience cumulatively in the Delta. And if you look at the 7 people on this committee, they probably have about 2 centuries worth of cumulative research experience in the low salinity zone and the Bay and the Delta. I have 4 years of experience, so asking to summarize and give you recommendations is a bit daunting. The one thing I was going to initially do is to basically recapitulate some of the main points that we made 2 years ago when we were presented to you. I think I'm going to forego that in the interest of time. This information was relayed to you in 2010 by the earlier panel. And I think I'll go ahead and just move in then to making a few comments about what you've heard this morning. And I'll start with some of the take-home messages that I heard from today's presentations, what resonated with me. And then I'll go on and talk just a little bit about some guiding principles that are being used in these kinds of decision-making elsewhere. And I'll also talk a little bit about some of the key new information that has been highlighted by the presenters since the 2010 meeting. And then finally end with sort of my personal take on this issue. So let me go ahead and just briefly highlight the 4 presentations to you. Bill Fleener, who talked about hydrologic changes, I think basically made an important point. And that important point from my perspective is that it's the combination of habitat loss, increased consumptive water use, decreased inflow to the Delta and outflow to the Bay, water quality degradation, interactively together, that produces the current stresses that are on the system that you're considering what to do about water flows and regulations moving forward. The second thing that Wim Kimmerer, I think, pointed out in his Ecosystem of Low Salinity Zone Changes presentation is that the habitat that represents this low salinity zone is dynamic in space, and it's both a system that has physical constraints by the engineered structures we have in the Delta, but it's also this very strongly tidally driven system that is moving on various time dimensions, everything from days to seasons to annual differences. He also, I think, pointed out that that low salinity zone, unlike many estuaries around the world, is now an area that's being subsidized both by the Bay and by the Delta. Many low salinity zones in other estuaries is actually an area of high productivity. Not true currently in the Delta in which we work. The other point that he made, and I think is an important one for the board to hear, is beware of simple correlative relationships. They rarely tell the whole story, and I think that's an important take-home message. Jim Klein, managing the estuary for an uncertain future, I think he showed us nicely that both human actions and climate variability impart major transformations to estuaries. So we're talking about things that are happening not just locally, but also at very large scales. He also, I think, made some very important points about science contributing to managing the estuary, both through anticipating change and by informing adaptation. And I think that's an important take-home message for the board. And then he made a plea for strengthening the coupling between policy, modeling, and monitoring research. And I certainly echo those ideas and those comments. Anke Mueller-Solger talked a little bit about changing science with a very strong focus on the fall low salinity habitat study that has just been carried out recently. I think she shows us the importance of applying adaptive management to the estuary. The Delta Stewardship Council and the legislation that created the council requires that adaptive management be used as we move forward in a lot of our decision making relative to the Delta. My personal experience in working on these kind of problems has been predominantly outside of California. I've worked on these kind of issues in Florida, I've worked with colleagues in Australia, and I've come across some recent interesting examples of people trying to do these kinds of things in South Africa. So I want to just highlight a couple things. I'll start with Florida. That's where I've worked for 20 years. Florida passed a statute in 1972 that states the minimum flow for a given water course shall be the limit at which further withdrawals would be significantly harmful to the water resources or ecology of the area. And defining what significantly harmful is has been the big challenge for them. But they have been at this, setting flows, mostly for rivers, although I pointed out to some of my colleagues they have done an estuary or two now. They've been basically trying to figure out how best to proceed with this. And the way that they've done this is to realize that the hydrograph has various portions of it that probably need to be considered differentially. So they use what is called a building block method. So they basically take periods of time, for example, like really critically low flow periods, periods of base flow, periods of changing flow, periods of high flow, block that into different segments, and then begin to consider what the flow requirements would be in each of those blocks. And they actually do this with a daily time step, something that we rarely see here in California, where it tends to be often done in a monthly time step. Australia has some interesting principles that they're using in setting their flow criteria, highly contentious, as you probably well know. I'm going to skip over those in the interest of time, and I'm going to move on to the ones that are being used now in South Africa. I find them of interest. They have 8 guiding principles that they use. I'm only going to highlight the 4 that I thought were maybe germane here. But they have been using these kind of things to help guide their setting of flow criteria. This is a byproduct of the post-apartheid constitution, which requires in South Africa that basic water needs are the first priority. The second priority is the environment, and the third priority is agriculture and industry. So basically, the wrestling with how to set these kind of flow criteria has been a very big issue for now about 15 years in South Africa. Here are some principles they've settled upon. First one is a modified flow regime should mimic the natural one so that the timing of different kinds of flows is preserved. The second principle that they're using is the first flood of the wet season after the dry season should be preserved. The third one that they use is that floods should be present during the natural wet season, but not necessarily all floods, and they may actually even be truncated in duration, so you can extract more usable water. The fourth one that they have is most water should be harvested during the wet periods, and that little water should be taken during the dry periods. So these are some principles they're using in trying to deal with flows and producing a water supply for human need, for agriculture, and for industry. So the board asked us to think about what's gone on in the last 2 years. I think you've heard a number of good examples from the panel. I won't dwell on that. Let me just finish with sort of my thoughts on what I've heard today. And first of all, I do believe that flows do matter for streams, rivers, and estuaries. I think there's been many decades of cumulative research in these types of ecosystems that show the importance of flows. I think you're going to find that during these 2 days of your workshop, you're going to hear everything from flows are the master variable to flows are unimportant. And I think really you should be thinking of this in a middle ground. It's not a master variable. It's not the only thing to be considered. It's certainly not unimportant either. So flows, I want to emphasize, interact with a number of other things that need to be considered in this estuary. They interact with contaminants. They interact with nutrients. They interact with predators. They interact with the non-native species and the native species that we have in the system. They interact with these types of habitats that are now present within the system. They affect turbidity. They affect harmful algal blooms by the residence time of the waters and what's in the waters. And there are many other stressors that flow interact with. So my final comment to you is that flows and flow criteria deserve your consideration. Thank you.
Thanks very much. If you guys have questions for any of the panel members, feel free. Pardon me?
Let's start with staff,
Okay.
because I know they have come up with some questions that, that they're interested in. Did you?
I can let them go first.
Okay. And if you just want to punt back.
Well, I mean, I
that's
guess
fine.
we've talked a lot about uncertainty and formats for actions that the board should be taking. Does the panel have any specific recommendations for what we could be doing in the next couple of years to move forward in our planning process? So, and maybe put another way, is there, we've talked a lot about all of the uncertainty that's out there related to, you know, the science. Is there any certain actions that the board should be taking that are clear and need to be taken, you know, in the short term?
I'll posit at least one point, and that is I think Jim Klern's idea of linking policy, linking the modeling and the modeling community's capabilities with monitoring research more effectively as you're gathering information for your decision making is something that ought to be implemented right away.
I'll just restate the point of my presentation. Is it on? Okay. I'll just restate the point of my presentation, and that is we need to institute processes that don't exist.
And I guess I will chime in. The flash studies that Anka described were very, very interesting, very valuable. Results are still coming in. They were a chance to really check our hypotheses against a condition out there. That condition hadn't happened for 15 years. It used to happen every year that was wetter above normal, and that was why it was called for in the biological opinion. But doing adaptive management actually, I think, requires stepping in and doing something. Because if we simply step back and wait for the next time that we happen to be blessed with a sufficiently wet year to produce those conditions, it now has to be so much wetter than it used to need to be, that we would have to wait another 15 years. And our N would then go up to 2, which still wouldn't be very satisfying. So I would use that as an example of where we have some uncertainties that have some very clear questions associated with them. Does this action increase productivity in the low salinity zone? That was one thing we went and looked at. Does it affect growth? So we could actually look at things. And I would urge the board to push in either as in whatever forum you might, to make those kind of conditions change out there. Anka's picture of the estuary for the last, and WIMS, was of a very stable system out there, and how that stability has favored species that we don't much care for, Garrya, Microcystis, and others. Going in and making sure that some of that variability happens is good. Making sure some of that variability happens in association with studies to see why that variability might be useful is something that we can try to do in the short term. And I would urge the board towards that. I know that you are thinking about a percent unimpaired flow, and that doesn't do the job that we've been describing. But using that tool to say, this year we're going to take this percentage of unimpaired flow and use it to produce these conditions to test these uncertainties, that would be a very useful thing. And if 2011 was any indication, you can expect remarkably rapid
feedback. I am just floored by how much those tested hypotheses where we actually got something, oh yeah, that worked, or we got enough data to say we need to change that in 2012.
I have a follow-up with Jim. In recommending that there be a tighter nexus between policy making and the modeling and a lot of the science work that's being done, and then that was added to it, the adaptive management element, and you say it's weak now. Is it weak largely because of the location of each of these activities? They don't communicate with one another. What makes this connection so weak? And the corollary, you know, what changes need to happen that would strengthen them, short of creating another, totally new institution, which might be hard?
Well, first of all, the weakness of these couplings isn't unique to California and policy science connections related to the Bay Delta. This is a universal problem, and we're struggling with this at the national level, and we're struggling with this at the regional level. I'm such an optimist about California. If California I think California has an opportunity to lead the way in finding ways to strengthen these couplings. I think, in my view, this seems to be a task that falls perfectly in the purview of the Delta Science Program, and I think with sufficient and appropriate support, they can take on this task. And there are lots of different things that could be done through, for example, shaping requests for proposals so that so that new science meets your information needs. We really need to get the communities of scientists talking to each other who do the observational program and the modeling. The way it works right now is observations are used to calibrate and verify models, but I'm not sure that we've done as good a job as we can of making sure that our monitoring programs are measuring the right things at the right times at the right places to detect the kinds of changes that we're anticipating. I think it might be useful to hear from, we're fortunate we've got the current lead scientist and the past lead scientist, what their thoughts are about the role of the Delta Science Program in taking this on. But it seems to me that we've got an entity that can do this with the right resources. And there isn't, as far as I know, a really good template anywhere for us to follow. I could be wrong about that, but why don't we create that template?
Did I see another question over here? And then we do need to take our break, so go ahead.
Good. Well, thanks for reminding us of all the moving parts, esteemed invited panel. I guess through reading all the materials submitted, one of the sort of advisory statements that I thought was important was careful about the assumption of hydrologic stationarity. I didn't know stationarity was a word, but the idea that we can use existing flow data to sort of predict what kind of outcome we'd be looking at. And I think Mr. Claren's submittals and recent work highlight the dynamism of the underlying system. And that's in contrast to the existing Bay Delta plan, which is really what we're here to talk about, is we have an existing plan and what modifications are appropriate. We just heard some interesting ideas from Mr. Herbold about, well, should we take on some dimension of the plan that encourages us to do collaborative management and measurement and adaptation? That's an interesting concept that I kind of like to park over into my parking lot. But getting back to what the Bay Delta plan has, it has a lot of dimensions of variable hydrology built in, but the underlying